Hello, everyone. Thanks for tuning in. My name is Peter Adler. I'm a plant ecologist at Utah State University, and I'm going to give you an update on what the theory working group has been up to. Our goal is to learn when, where, why, and how is nature predictable. We expect that some ecological processes are easier to forecast than others. We want to identify those cases, but we also want to understand why forecasting is easier in some systems than in others. Answering this question will help focus applications on the most tractable problems, but our answers will also advance basic ecological research. They'll allow us to benchmark our current understanding and motivate novel comparisons across subdisciplines. So how do we do it? One approach is to compare many different forecasts from many different systems. This is an inductive or bottom-up approach. This is where our working group got started, and we quickly got into the specifics of exactly how to compare different forecasts. What kind of data and metadata would we need? The forecasting standards group is now pushing forward on that front, so I won't talk about it anymore today. A second approach is deductive. Given our current understanding of ecological dynamics, can we develop a priori hypotheses about when and where nature is more and less predictable? It turns out that this is not so easy. I wish I could just show you a list of the hypotheses that we've developed. Instead, I'm going to describe 3 lessons that we've learned that we think are helping us to move closer to those system-specific hypotheses that we ultimately want. The first lesson is that a common vocabulary is really critical. Forecasts can vary in spatial, temporal, and phylogenetic scale, and making comparisons is virtually impossible without being very explicit about these scales. One dimension of temporal scale is the length of the period being forecast. This led us into discussions about the difference between the forecast horizon and the forecast limit. We've also spent time parsing the difference between predictability and model transferability, and we still haven't agreed on a crisp definition. The clear importance of scale led us to a second lesson, that sources of uncertainty probably depend on scale. So I'm showing you a figure that's based on Mike Dietz's 2017 paper in Ecological Applications. It makes 2 key points. First, to compare predictability across systems, we should focus on the rate at which uncertainty or forecast error increases as we move away from initial conditions. Second, that rate depends on sources of uncertainty, such as initial condition, exogenous drivers, parameter uncertainty, parameter variability, and process error. Down here on the x-axis, you can see the implication that this all depends on something about scale. So inspired by our vocabulary debates, Christy Rawlinson thought that we should make those scales explicit. So here we're showing which drivers of uncertainty will dominate at different forecast horizons, that's on the x-axis, and at different spatial scales on the y-axis. We expect that initial conditions should dominate short-term dynamics across spatial scales, and that this influence may last longer at large scales where endogenous stability is stronger. For the longest forecast horizons, uncertainty should be dominated by exogenous drivers like climate or land use change. Most of the forecast horizon is dominated by process uncertainty, which reflects both parameter uncertainty as well as heterogeneity and random effects. The third lesson is that successful forecasting requires considering how the scale of the forecast relates to the scale of key ecological processes. For example, if we want to predict population dynamics over very short forecast horizons, we clearly need a model that accounts for the influence of weather on birth and death rates. If we want to predict population dynamics over much longer timescales, we may also need to account for slower processes, ecological and evolutionary selection, or turnover of other species in the community. So to make this specific case more general, we tried plotting forecast horizon on the x-axis and the timescale of key processes on the y-axis. Now on this 1-to-1 line, this is where the scale of the forecast horizon matches the scale of the driving process. And perhaps this is where we can make better predictions. Perhaps the farther away we go from this 1-to-1 line, the less predictable things get. But maybe this relationship isn't symmetrical as I'm showing. Below the 1-to-1 line, the forecast horizon is longer than the driving process. And maybe this leads to better forecasts than the opposite case, where the forecast horizon is shorter than the key process. Now, if you find this kind of question interesting, then please join us. As you can see, we can use all the help we can get. There's plenty of opportunities for people to contribute. Thanks for listening.